Good day dear students, in this video we shall see about the simple problems on beam elements. Simple problems for this module 3 will be solved in this video. So in this slide we are having a problem. So figure shows a simply supported beam subjected to a uniformly distributed load, that is UDL. Obtain the maximum deflection. Consider Young's modulus as 200 gigapascal and moment of inertia I is 2 into 10 power 6 millimeter mm to the power 4. So figure is given. We have a simply supported beam. So one end is fixed and another end is free to move in x-axis. So 12 kilonewton per meter is the load acting throughout, and 1 meter is the length of the beam. So let us write down the known details. So E is equal to 2 into 10 power 5 Newton per millimeter square. So let me convert it into kilonewton per meter square. So it is nothing but 2 into 10 power 5 into 10 power 6 divided by 10 power 3. So it becomes 2 into 10 power 8 kilonewton per meter square, or 2 into 10 power 8 kilopascals. Okay. So next I is 2 into 10 power 6 mm to the power 4. So I am converting it into meters. So 2 into 10 power 6 mm to the power 4 is nothing but 2 into 10 power minus 6 meter to the power 4. So E into I, so modulus of elasticity into I will give me 400 kilonewton meter square. So writing down the finite element model of the beam element, we have two nodes, node 1 and 2, 1 meter apart. So at node 1 we have m1 theta 1 and m2 theta 2 at node 2, mu1 f1 at node 1 and mu2 f2 at node 2. So the element stiffness matrix is given by the formula K is equal to E into I divided by L into 12 6L minus 12 6L 6L 4L square minus 6L 2L square minus 12 minus 6L 12 minus 6L 6L 2L square minus 6L 4L square. So only one element is there, hence the element stiffness matrix itself becomes the global stiffness matrix. So the length of the beam is known, 1 meter. E and I value have already been calculated in the previous slide. So substituting the values for E, I and L in this matrix, we get the elemental stiffness matrix. So the elemental stiffness matrix is written as K1 is equal to 400 into 12 6 minus 12 6 6 4 minus 6 2 minus 12 minus 6 12 minus 6 6 2 minus 6 and 4, which pertains to mu1 theta 1, that is at node 1, and mu2 theta 2 at node 2. So the global displacement vector can be written as mu1 theta 1 mu2 theta 2, and the force vector can be written as f1 m1 f2 m2, that is load and moment. So load at node 1 is PL by 2 and moment is P naught L square divided by 12. Similarly, load at node 2 is given by the formula PL divided by 2 and moment is given by the formula minus P naught L square divided by 12. So the load value is given 12 kilonewton per meter acting in downward direction, hence the sign convention will be minus. So substituting this and getting the force matrix, we get force matrix or load vector has minus 6, minus 1, minus 6 and 1. We know that at equilibrium K into Q is equal to F, or the stiffness matrix multiplied by the displacement vector will give us the force vector. So the value of K has been generated previously. The value of Q matrix also has been written down. So substituting this in the equation for the equilibrium condition, we get K into Q equal to F. So 400 into 12, 6 minus 12 6, 6 4 minus 6 2, minus 12 minus 6 12 minus 6, 6 2 minus 6 4 into mu1 theta 1 mu2 theta 2 is equal to minus 6 minus 1 minus 6 and plus 1. So applying the boundary condition, we know that mu1 and theta1 and mu2 is equal to 0, because at node 1 it is completely fixed. It cannot move in either x-axis or y-axis. At node 2, x rotation is allowed. Hence theta 2 will not be 0. All other values are 0. So by using the elimination method, we will be able to write that 400 into 4 into theta 2 is equal to 1, or theta 2 is equal to 6.25 into 10 power minus 4 radians. So the displacement vector can be written as q is equal to 0, 0, 0, 6.25 into 10 power minus 4 radians. So next step is to find the maximum deflection. So we know that mu is equal to h into q, where h is the Hermite shape function and q is the displacement vector. So the Hermite shape function, we know that there are 4 variables, h1, h2, h3 and h4. So writing down the equation, mu is equal to h into q, where mu is equal to h1 mu1 plus le by 2 into h2 theta 1 plus h3 mu2 plus le by 2 h4 theta 2. We know that mu1 is 0, theta 1 is 0, mu2 is 0. Hence only the value of h4 Hermite shape function is required, which will be written as le mu max or maximum deflection is equal to le by 2 into h4 is nothing but minus 1 minus zeta minus zeta square plus zeta cube divided by 4 into theta 2. Substituting the values, we get maximum deflection as 7.8125 into 10 power minus 5 meters. So this is a step-by-step list of the exercises that you need to carry out for solving a problem. So first thing that you are supposed to do is discretize the problem by creating the nodes and the elements. So if there are 2 elements, then there will be 3 nodes. Okay, so you have to discretize the problem or break down the problem. Next, calculate all the variables, that is modulus of elasticity E, modulus of elasticity or Young's modulus E has to be calculated, moment of inertia is to be calculated I, length of the element LE has to be calculated. Next, calculate the elemental stiffness matrix K using the formula. Next, add the elemental stiffness matrix to get the global stiffness matrix capital K. So capital K will be K1 plus K2 plus K3, whatever it is. How many elemental stiffness matrices are there? You have to add up all those things to get the global stiffness matrix. Next step is to calculate the global nodal displacement vector Q. And after that, once Q is found out, Q is nothing but mu1 theta 1 mu2 theta 2. So once Q is found out, that is global nodal displacement vector is found out, calculate the global load vector F, or the force vector. So F1, F2, F3, F4 is to be calculated. Once that is done, applying the equilibrium condition wherein K into Q is equal to F, that is displacement into stiffness of the element, will give us the force that is acting. So applying the boundary conditions and removing the unnecessary rows and columns, we can reduce the equation to solve for the unknowns. So calculate the unknown variables, have step number 9, and finally calculate the deflection. Mu is equal to h into q, where h is the Hermite shape function and q is the deflection or displacement vector. So you get the maximum deflection by using the formula h into q. So these are the steps involved in solving a problem for a beam element. So let us see next problem. So problem number 2. solve for vertical deflection and slopes at point number 2 and 3 using the beam element for the structure shown in the figure. Also determine the deflection at the center of the portion of the beam that is carrying the UDL. So here you can see node 1 it is completely fixed, node 2 it is free to move in x-axis, node 3 also it is simply supported with the roller supports. So you can clearly see 3 nodes, 2 elements are there. For element 1 the length is 1 meter, for element 2 also the length is 1 meter. Modulus of elasticity is 200 gigapascals throughout for both element 1 and 2. Moment of inertia is 4 into 10 power 4 millimeter to the power 4. So now using kilonewtons and meters as the units throughout. So whenever you are solving, you have to always take care of the uniformity of the units. If there is any slight variation in the uniformity of the units, you will get wrong answers. So if you are maintaining kilonewtons, you have to maintain kilonewtons throughout. If you are maintaining meters, you have to maintain meters throughout. So E is nothing but 200 gigapascals, so 2 into 10 power 11 by 3, that is 2 into 10 power 8 kilonewton per meter square. I is 4 into 10 power 6 millimeters per 4 or 4 into 10 power minus 6 meters to the power 4. So E into I will give us 800 kilonewton per meter square. So writing down the finite element model of the beam element, we get 3 nodes, 2 elements, M1 theta 1 at node 1, M2 theta 2 at node 2, M3 theta 3 at node 3, mu1 F1 at node 1, mu2 F2 at node 2, mu3 F3 at node 3. So comparing both the figures, we clearly understand that L1 is equal to L2 is equal to 1 meter and the distributed load P0 is minus 12 kilonewton per meter acting in downward direction, hence the negative sign. So the elemental stiffness matrix for the beam element can be generated. There will be 2 elements, hence 2 elemental stiffness matrix. So we will see the elemental stiffness matrix in the next slide, K1 and K2. So K1 value 800 by 1 cube into 1 is nothing but the length of the material. So it comes to K1 into 12 6 minus 12 6 6 4 minus 6 2 minus 12 minus 6 12 minus 6 6 2 minus 6 and 4. Similarly K2 also will be same because the length is same, modulus of elasticity is same and moment of inertia is also same, hence the K2 value also will be equal to K1. Now while generating the global stiffness matrix, we have to add both K1 and K2. So we have to, it is clearly observable that node 2 is common for both element 1 and element 2. Hence mu2 and theta 2 is present in both the stiffness matrix, that is K1 and K2. Hence these two mu2 and theta 2 will be added up in the global stiffness matrix. So it will become 12 plus 12, that is 24, minus 6 and plus 6 will become 0. 6 plus 6 becomes 6 and minus 6 again becomes 0. 4 plus 4 becomes 8. 4 plus 4 becomes 8. And the global stiffness matrix is represented in the matrix form below. So in the next step, the global nodal displacement vector Q is equal to mu1 theta 1, mu2 theta 2, mu3 theta 3, and F is equal to F1 M1, F2 M2, F3 M3. So since only 2 elements are there, it is subjected to uniformly distributed load, and the load vector due to UDL for the beam element can be calculated for element 2 as P naught LE by 2, P naught LE square by 12, P naught LE divided by 2 and minus P naught LE square by 12, which will come to minus 6 minus 1 minus 6 and plus 1. So the global force vector becomes 0 0 minus 6 minus 1 minus 6 plus 1. At the equilibrium condition, we know that K into Q is equal to F. Hence, K is the stiffness matrix, Q is the displacement vector, which is equal to the force vector. So substituting this and writing in the matrix form, we get the matrix as shown in this slide. So the next step is to apply the boundary conditions and eliminate all unwanted details. So from the figure, it is clearly evident that boundary conditions mu1 theta 1 is equal to 0 because it is fixed. Mu2 theta 3 mu1 theta 1 is equal to 0, mu2 mu3 is equal to 0 because it is vertical movements are constrained. So using the elimination method of handling the boundary condition and eliminating the corresponding rows and columns for mu1 theta 1 mu2 and mu3, we get the matrix reduced as 800 into 8224 into theta 2 theta 3 is equal to minus 1 and 1. So two unknowns, two equations, we can solve for it and get the value of theta as minus 0.2679 into 10 power minus 3 radians and 0.4464 into 10 power minus 3 radians. So the nodal displacement vector will be written as 0 0 0 minus 2.679 into 10 power minus 4 0 4.464 into 10 power minus 4. So this is the answer for the nodal displacement vector. Next, to find the maximum deflection at the midpoint of element 2. So mu is equal to h into q, where h is the Hermite shape function and q is the displacement vector for element 2. So this we will solve and get the values in the next slide. So mu is equal to h1 into mu2 plus half le h2 theta 2 plus h3 mu3 plus half le h4 theta 3. So h1, h2, h3 and h4 are the Hermite shape functions of the beam, and at midpoint mu is equal to 0, and from the boundary conditions at midpoint zeta is equal to 0, and from the boundary conditions mu1 mu2 is equal to 0. So substituting all these values in the Hermite shape function, we get mu max is equal to le by 2 h2 theta 2 plus le by 2 h4 theta 3, and substituting the values of zeta theta 2, we get maximum deflection as 0.0893 into 10 power minus 3 meters. Okay, this is problem number 3. So for a beam element shown in the figure, determine the end reaction and deflection at mid span. Consider E is equal to 200 gigapascals and I is equal to 4 into 10 power 6 millimeter to the power 4. So we will write down the data that has been given. We have E 2 into 10 power 5 Newton per millimeter square, which converts to 2 into 10 power 8 kilonewton per meter square. I is 4 into 10 power 6, which converts to 4 into 10 power minus 6 meter to the power 4. So E into I will get 800 kilonewton per meter square, kilonewton meter square. Now writing down the finite element model for the beam element. So clearly it is evident that there are two elements, 3 nodes. So for element 1, the UDL is 12 kilonewton per meter, and for element 2, the UDL is 24 kilonewton per meter. So let M1 theta 1 mu1 F1, M2 theta 2 mu2 F2, M3 theta 3 mu3 F3 be the deflection load vectors at node 1, 2 and 3 respectively. So it has been mentioned, it has been shown in the diagram. So the stiffness matrix is K is equal to EI by L cube. So it will be considered as 12 6L minus 12 6L 6L 4L square minus 6L 2L square minus 2L minus 6L 12 minus 6L 6L 2L square minus 6L 4L square. So L1 is equal to 4, L2 also is equal to 4, and E and I are same. Hence K1 will be equal to K2. So for the element 1, the elemental stiffness matrix we will get as 12.5 into 12 24 minus 12 24, 24 64 minus 24 32, minus 12 minus 24 12 minus 24, 24 32 minus 24 64. So K1 will be equal to K2. Now we have to observe that the values of mu2 theta 2 will be repeated in the values of in the stiffness matrix K2. Hence mu2 theta 2, that is 12 minus 24 and 64 will be added with the 12 plus 24 plus 24 and plus 64. Hence it will become the values at the node 2 will become 24 0 0 and 128. So this will be observed in the next slide. So as explained in the previous slide, we can observe that K1 and K2 are added up to get the global stiffness matrix K, and you can observe that mu2 is 24 because of adding up with the 12, and it is theta 2 is 0 because adding minus 24 and plus 24. Again mu2 theta 2 is 0 adding up plus 24 minus 24 and plus 24, and theta 2 is 128 because we are adding 64 plus 64. So global stiffness matrix has been deduced. So now calculating the displacement vector Q, which is equal to mu1 theta 1 mu2 theta 2 mu3 theta 3, which is equal to PL by 2 into PL by 2 at node 1, and theta 1 is PL square by 12, mu2 is again PL by 2, and theta 2 is minus PL square by 12 for element 1. Similarly for element 2 also we have to calculate the load vector and then add up the both. So F1 is nothing but minus 24 minus 16 minus 24 plus 16, which corresponds to mu1 theta 1 mu2 theta 2 for element 1. Here you can observe that P0 value is minus 12 kilonewton per meter, whereas for element 2 the P0 value will increase to 24 kilonewton per meter. Minus signs indicate that the load is acting in the downward direction. So here you can observe for element 2 the load vector is minus 48 minus 32 minus 48 minus plus 32. So now adding the both the vectors, we have to observe that mu2 and theta 2 is present in both the load vectors, hence it has to be added. So it becomes minus 24 minus 16 minus 24 minus 24 minus 16 minus 24 plus minus 48, that comes to minus 72, plus 16 minus 32, that comes to minus 16, then minus 48 plus 32. The same thing is written in the global force vector. So next is applying the equilibrium condition. So equilibrium condition, we know that stiffness into displacement is equal to the load vector or the load that is acting. So K into Q is equal to F. So applying the formula K into Q equals to F, we get the 6 into 6 matrix. Now we can apply the boundary condition. We know that mu1 theta 1 mu2 theta mu2 mu3 is equal to 0, because it is clearly evident from the supports that there is no deflection, there is no free movement at node 1, whereas at node 2 and node 3 there is deflection, theta is allowed. Hence theta 2, theta 3 is not 0. All other values are 0. Hence we can remove the column 1, row 1, column 2, row 2, column 3, row 3, column 5, row 5. Column 4 and row 4 and column 6 and row 6 will remain. So it will reduce to 2 into 2 matrix. So two unknowns, theta 2 and theta 3. Solving we get theta 2 to be minus 0.0228 radians and theta 3 to be minus plus 0.0514 radians. Now to find the maximum deflection, we have to multiply the Hermite shape function with the deflection matrix. So which is equal to mu max is equal to h into q, that is h1 le by 2 h2 h3 le by 2 h4 into q. So h1 h2 h3 and h4 are the Hermite shape functions for the beam. So writing down the formula for the same, and QE is the elemental displacement vector. So direct substitution, we get the values for element 1. Mu1 is 11.4 millimeters. Similarly, substituting the values for element 2, we get the deflection to be minus 37.11 millimeters at the center. So next step is to calculate the reactions. So reactions at any given point is given by the formula K into Q minus F. So the stiffness matrix is known, Q is known, load acting F is also known. So for element 1 we will be substituting the formula for the reactions for element 1. So R1, R2, R3 and R4 are to be found out, and 4 into 4 stiffness matrix for element 1 and the displacement of element 1 and force vector for element 1 are substituted to calculate the reactions, and we get the reactions for element 1 has 17.16, 6.88, minus 30.4 and minus 34.24 in kilonewtons. Direct substitution and calculations. Okay, this is problem number 3. So for a beam element shown in the figure, determine the end reaction and deflection at mid span. Consider E is equal to 200 gigapascals and I is equal to 4 into 10 power 6 millimeter to the power 4. So we will write down the data that has been given. We have E 2 into 10 power 5 Newton per millimeter square, which converts to 2 into 10 power 8 kilonewton